Hi, thank you so much for watching. This is a recorded presentation for our ECE 6960 Deep Learning project presentation for the semester. This is spring 2020. My name is Jacob Nissanen, and my project partner is James Jones. You'll see him later demoing our project for you. Our project is a Connect 4 robot that plays the game Connect 4 using reinforcement learning to learn how to play. And we also compare that versus more traditional or earlier methods of just training a model based on supervised learning. So I'm excited to show this to you. We've worked really hard on this. Oops, there we go. So just as an introduction for this project, so in a lot of sort of gameplay research and how machine learning helps with that, Go is a popular board game for this. It's a popular battleground for developing and testing machine learning networks, mostly due to its complexity. It's a complex game with an estimated 10 to the 127 possible board states. So there's a lot of possible board states, and there's no way that there's an easy algorithm to determine what's the best move to play. Our project is heavily influenced and motivated by the AlphaGo Zero program. It's a paper that was published by David Silver and many others, where they took more traditional learning methods that had used supervised learning, where the models were given expert game moves to learn from, and then a little bit of self-play. AlphaGo Zero, they trained completely on self-play. From a blank state without telling the game any strategies or any expert moves or anything like that. And it outperformed the previous versions of AlphaGo significantly and beat them every time. So our motivation was to replicate that same thing. Oops. Yeah, our motivation was to repeat the same experiment with using AlphaGo Zero's methods of reinforced learning and self-play, and mimic the same performance on a more simpler game. We did that with a game called Connect 4. It's a game with the grid that you see here. It's a vertically suspended grid with 7 rows or 7 columns and 6 rows. You drop different color tokens. Each player represents a different color, and whoever gets a 4 in a row, either vertically, horizontally, or diagonally, whoever gets a 4 in a row first wins the game. And you do that by dropping tokens into the individual columns. It's a less complex game for sure, but it has been calculated that it contains over 4 trillion unique boards. So it's by no means a simple game, but it does add a lot more simplicity than Go, for example. But our project also wanted to take this a step further and add hardware to be able to interact with our models that we had trained previously. So it's a lot of software, of course, train the models and get a system working that can also interact with hardware and be able to play a game using those reinforced learning and the supervised learning models. So our project created 2 separate kinds of players to repeat the same experiment. One of them was with supervised learning models, which we had only fed with expert game moves. And then the second is the reinforced learning model, which we used AlphaGo Zero's method and used self-play to iteratively generate better and better players. So we'll go into more detail on these 2 here, starting with the supervised learning model, which we actually used LSTM models for. We used 2 models for them, one for each player. So depending on if you drop a red token or a yellow token, or for player 1 or player 2 respectively, we trained separate models for. And we used a 2-layer LSTM model for each one, which contained 55,143 trainable parameters each. As each of their data sets, we used 1 million boards and expert human moves to train each of them. So total, we created 2 million unique boards and their corresponding expert moves. We created the expert human moves using the alpha beta pruning algorithm, which is an optimization over the minimax algorithm, to determine what would be the optimal column to drop a token into. So we use that to create 1 million boards and 1 million corresponding expert human moves for those. We trained each model for 1,000 epochs with a batch size of 8,192 boards each. Our accuracy was 98%, and the loss MSE was 0.05 on the training set. Now, as far as the data set itself, of course, like I said, we use the alpha beta pruning algorithm. We did that with a depth of 4. The input to these LSTM models is a one-hot encoding of the board. So there's 6 rows and 7 columns, so you've got 42 cells. And then there's, of course, 3 possible states for each cell, whether it's empty, whether it's got a red token, or a yellow token in it. So 3 states, we one-hot encoded the board as our input. And then our output is a one-hot encoding of all the actions, which are only the columns. You can only drop tokens into the columns. So that was our output, a one-hot encoding of those columns. As far as our reinforced learning model, it's a lot more complex. Again, we adapted a lot of what we did from AlphaGo Zero's paper, simplified it a little bit more for our needs. But it is a single model with 2 outputs. So we created one model with a single input that created 2 separate outputs. The outputs are a policy and a value. Now the policy is an array of move probabilities for selecting each column. So the probability that you should select each one of the possible columns. And a value is just a scalar for the probability of the current player winning at the current board. So in this much more complex model, it contains multiple convolutional and residual blocks. For that, we refer you to our report or to our paper for the specifics on the parameters for those blocks and those layers that we use for the model. So we'll refer you to those. But the input to the model is a hash value of the flattened board. So it's a single hash value that's created from flattening the array of the 6x7 array of the board. In total, it's got nearly 400,000 total trainable parameters in it. And to do that, so the data set is constantly being created. It's an iterative cycle between creating a data set and training the data set and then testing. Sorry, I'll restart that. Creating the data set, training the current player, and then testing that player against the currently termed best model. And then it repeats that cycle of creating data sets, training, and evaluating. And then if the currently training model terms to be better than the previously quoted best model, then it substitutes and it repeats until you get iteratively better and better models. So we did that using some long-term and short-term memories. I'll start with the short-term. The short-term memory is just all of the moves that have been played and then their resulting outcomes that have been propagated down through the rest of the plays that have been previously made in the game. So at the end of every game, the short-term memories gets transferred to long-term. The long-term memory is a queue. It's a fixed length queue of 20,000 memories or 20,000 moves and their corresponding resulting outcomes. And so the long term is used to train the model better and better, and it constantly gets refreshed with newer and more current memories. The best moves are chosen using the Monte Carlo tree search algorithm. It's a really nice algorithm for determining the best move of a ever expanding tree, where in this case you've got over 4 trillion possible boards, so there's no way you can search through all of those. So the Monte Carlo tree search algorithm does a great job of expanding that. And for more information, there's some great discussions on what that is about, and then we include some of that in our paper as well. We allowed our model to self-play for 15 days, and I'll get into the results later, but we're very proud of our results. So we let it play for 15 days. 10 days of that was on my own little MacBook to see how well it was playing. And then once we determined that it was getting better and better, we switched training over to an NVIDIA Jetson Nano and let that play for 5 more days. And it got significantly better being on the Jetson Nano for a little longer. But before I get anything else, I'd like to show a demo of it. James has created a video for it. I'll just play that video now. He'll show you the full hardware setup, and he'll explain some parts of the hardware setup, and he'll even play a game against it himself. And you'll see him get frustrated with it because the reinforced learning model is the one he plays against, and it plays pretty well. It puts him in a couple pickles. So I'll play that video now.
Sweet. Hi, this is a demo of the Connect 4 robot. So before we get started, I think I'm going to go over a little bit of the hardware. Okay, so what we have here, obviously we have the game board right there, and the computer already played its first move. There are Jetson right here, a little bit of a mess of our cables here, all the wiring and everything over there. Hoppers right here, and then we have our stepper motor over on here, and then our tensioner, belt tensioners right there. And we also have, there's the support rod that goes across the front. Servos are in the back right there. You can see them underneath there, just holding up some of those tokens on the top one there. Bottom one there, I don't know if you can see it underneath. Kinda, there it is. Yep, holding up that token right there. We've got our power supply here, stepper driver there, and there's the servo controller hanging up on the side over there as well. The gantry was built by myself, and we had to cut and mill a couple things. You can see I had to mill out a couple of holes there. I had to create a couple of extra little plates. All these plates right here had to be built, cut out, and drilled out. This black one right here supporting that. We had to do some milling on the actual stepper driver as well to mount it to the gantry. And then there's this other plate to mount as a power supply. So that's the overall setup. Now let's see if we can get a game going here. Okay, so this is using our reinforcement learning model, which is based off of AlphaGo 0, and it was trained for about 15 days. Now, it's not perfect, but it does really, really well. In fact, a lot of times it puts me in some frustrating checkmate-like positions that I can't get out of. So I'm going to go ahead and make my moves here. We'll see if we can make it through this game and see if I can beat it. Probably not, but we'll see. Well, dang it. All right, so something that you can see right here is that I wasn't thinking very clearly, and I put a tile here, and well, now he set himself up for 4 in a row there. If I try to get a tile here to get 4 in a row there. So, kind of a tricky situation. Okay, well, I just lost. There he goes. Done. So, I may not be a championship Connect 4 player, but it's pretty darn good. It blocks your moves, it sets itself up like to do crazy setups that are almost unbeatable. I mean, it plays in places that are like, why did you play there? And then you look at it for a while, or you play a couple more turns and you figure out, Holy cow. It's been setting this up for like 5 or 6 turns in a row here. It's pretty crazy. All right, so thanks for watching. And yeah, if you're interested, please contact me or contact Jacob with any kind of questions of what we got going on here and let us know. Thanks again.
So as you saw, the reinforced learning model beat James. It does really well, but we know by no means claim to be professional Connect 4 players. To compare our results to our LSTM models and see how well those performed comparatively, we played 100 games against each other, with every other game switching who starts first. And out of 100 games, the reinforced learning model beat it every single time within 12 moves, which isn't very long. It's only 12 tokens that are being dropped in a game where you only need 4 to win. So that was fairly quick. So it shows quite the superiority, and it also shows how AlphaGo Zero's techniques can be repeated for other games, just as they have shown. We also played against it as well, just to see how well comparatively it is, just like James showed. And we played hundreds of times. Luckily, we also have a built-in simulator in our code, so we don't have to hook it up to the hardware every single time, because the motor actions take a second or two, so it helps really speed up gameplay. But using our simulator, we played hundreds of times, both myself and James. We even had other people play it too to see how well they were. And out of everybody that we've had play, so hundreds of games, the reinforced learning model only lost once. Otherwise, it would beat myself and James and anybody else that played. And it did it really well. So we were really excited with our results to show that we can create gameplay that can play expertly, better than humans that can. But Connect 4 is an interesting game. It's unlike Go or like chess or other games where it's kind of 50-50 for every player. It's more like tic-tac-toe, where whoever plays first determines a lot of how the rest of the game will go. In our paper, we cite the source for this, but a few years ago, for a master's thesis, a guy performed mathematics on Connect 4 and determined that in perfect play, his name is Victor Alice, in perfect play, the first player always wins if he starts in the center column. So Connect 4 has some mathematics like that, which makes it different than other games. But it was encouraging for us because in our results, we saw that shortly into the training of the self-play, the reinforced learning model did start repeatedly in the center. So it wasn't long, it was maybe a few days before it started consistently playing in the center every single time. And so it was able to learn that fairly quickly. So it just helps validate our results further. But with that, it sparks the imagination for future work that could happen in this field, both with reinforced learning or experimenting with other forms of reinforced learning than what AlphaGo Zero demonstrated. For example, there's a thing called DQN, where it gives you possible rewards throughout the game, and the model learns to maximize those rewards. Some examples are seen in OpenAI Gym, where they play a cart pull game or an Atari game. Those would be very interesting to look at and to experiment with to get a good reward system, because Connect 4 is different than a lot of other games, where Connect 4, you only have one result, and it's only given at the end, where if you win or you lose. But there's other games, cart pull and Atari games are great examples because you get points throughout the game. So they're great inherently for that. But it would be really cool to see how the performance of creating a reward system for Connect 4 would apply to DQNs, and comparing their relative performances between that and a reinforced learning model. Other games as well. I mean, Connect 4 is purely off of skill. It's also a global game in that both players can see the current board. It's not like there's cards that are hidden or anything that's hidden from all viewers of the game. So it'd be interesting to see how reinforced learning could be applied to other games multiplayer games like 3+ player games and see how that would learn, or games that would have an element of luck to it to see how these techniques would also uh, develop and create strategies for other games. So there's a lot of exciting work that can be applied for other future projects. Um, that would be really cool to see. But with this, we'd have so many people to thank. Of course, reinforcement learning isn't a very simple concept or how to implement, but luckily there's a lot of tutorials and a lot of implementations online that have given us a lot of foundation for how we've written our code and applied it to Connect 4. Those are listed here. Please check them out because they give us some great foundations and understanding on how to build our own for our purposes of this project. And of course, the AlphaGo Zero published paper is the resource we refer to the most. Is very well written and very explanatory as well. Also check out our paper as we've written a lot more about the hardware and the actual individual files, that how the whole system interacts closely together between hardware and software. So we encourage you to check that out. And then also lastly, our professor, Dr. Kunshi Yu, who really helped us in narrowing our focus and giving us some avenues to do some research on as we dove deeper into this project. So we thank him for that. We ask for questions, but since this isn't a live presentation, hopefully all of your questions will be answered by looking at our report. So thank you very much for your time. Thanks for listening. And we've really enjoyed this project. Thank you again.